بسم الله الرحمن الرحيم. سنبدأ المحاضرة السابعة من مادة التبريد المخصصة لطلاب الساعات المعتمدة كورس نمبر 401. عنوان المحاضرة Review on Refrigerant Right Selection and pH Diagrams. التعرف على الاختيار الأمثل لوسائط التبريد وخرائط pH Diagrams. أهداف هذه المحاضرة: أولا سنقوم باستكمال بعض المسائل التي سقطت من المحاضرة السادسة نظرا لوجود عطل فني أثناء التسجيل والضغط. ثم سنتعرف على أنواع خرائط التبريد المختلفة للوسائط التبريد المختلفة pH diagram and their different presentation for refrigeration cycles. ثم سنتعرف على الإجراءات الايزنتروبيك والأدياباتيك وتمثيل الايزنتروبيك efficiency on pH diagram، وما أوجه الاختلاف ما بين الإجراء الأدياباتي والإجراء اللا عشوائي، والكفاءة التي تحدد نسبة الحيود عن الإجراء المثالي. Review the factors involved in the selecting the right refrigerant for an application. التعرف على الطرق المثلى لاختيار وسائط التبريد طبقا للتطبيقات المختلفة التي يتم استخدامها في دوائر التبريد ومضخات الحرارة. وبالتالي سنبدأ باستعراض عدد 6 شرائح من المحاضرة السادسة، ثم سنبدأ في موضوعات هذه المحاضرة.
This slide shows a presentation of the vapor compression cycle on both TES diagrams and PV diagrams. It should be clear that the cycle are working between two main pressures: low pressure in the evaporation, which may be named evaporation pressure or evaporator pressure, and high pressure side, which is named condensation or pressure of the condenser, as can be shown on both TS diagram and PV diagram presented here in this slide. It should be clear that a terminal temperature difference should be kept between the evaporator and the cold space to be refrigerated. The refrigerant in the evaporator must be lower than refrigerated space temperature. Also, the condenser temperature must be higher than the ambient temperature, at which will the heat be rejected from the condenser during desuperheating, condensation, and subcooling to this temperature of outside temperature, even using air, or later on as we can use water for cooling in associated with cooling towers and cooling water circuits. This slide also presents the vapor compression cycle on TS diagram and on PV diagram, and finally the pH diagram, on which we have switched the vapor compression from TS diagram and PV diagram to use this pH diagram as discussed before. It has its presentation on pH diagram is very accurate and more accurate than presentation on TS and PV diagram, such the process of the forming components in the evaporation and compression, condensation and expansion devices are shown on 3 lines, straight lines on pH diagrams. The process from 4 to 1, evaporation at constant temperature with a change of enthalpy. Then process from 1 to state number 2, compression inside the compressor, even using isentropic efficiency 100% for isentropic compression, or isentropic efficiency less than 100%, and the S will be increased during this compression stage. The third process is from state 2 to state 3 inside the condenser. Started from desuperheating from point 2 until reach the HG at condenser pressure on the vapor saturation line, then starting to condensate the refrigerant inside the condenser until reaches points or state number 3 at the vapor liquid line, which is equally with state number 4 in the enthalpy, and then the final process vertically presented from point 3 to point 4 by decreasing the pressure and the temperature using throttling inside expansion device, which may be expansion valve or capillary tube, using constant H process where H3 will equal H4. In isentropic compression, S1 will equal S2. In the evaporator, the pressure of point 4 is equal to pressure of point 1. Also, the condensation pressure equal to pressure of state 3 and state 2. However, the temperature of state 3 is corresponding to the temperature is equal to the corresponding temperature for the corresponding pressure, but the temperature of point 2 is the maximum temperature to be recorded in this cycle due to the discharge of the compressor, as mentioned before and as will be seen on the solved problems to be discussed in this lecture. Here we will start to solve a number of problems based on the vapor compression cycle. Problem number 1 is based on refrigerant R12, which works between -15 and 35 degrees Celsius as evaporator and condenser temperature respectively. Using pH diagram, you are required to estimate the COP, then a mass flow rate of refrigerant per ton, and number C, piston displacement per ton using volumetric efficiency 80% for the compressor. Number D, heat rejected in the condenser per ton. Number E, the ideal COP based on Carnot cycle. In this slide, we can find the steps of the solution after presenting the cycle on pH diagram using the evaporating temperature and the condensing temperature to get the corresponding evaporating pressure and condensing pressure, and presenting the two lines of this pressure, of the evaporating pressure, which contains point number 1 and point number 4 in the evaporator inlet and outlet, and also point number 2 and point number 3 on the condenser pressure, which is located on the condenser inlet and condenser outlet. To get the COP after we have getting all the enthalpies from the pH diagram of R12, as can be seen on this slide, after getting these enthalpies, H1 equal 345 kilojoule per kilogram, H4 and H3 are equal to 134 kilojoule per kilogram, as shown on this map on its lower part. Then the enthalpy of state 2 is equal 375 kilojoule per kilogram using constant S line starting from state 1 and going parallel through the constant S lines on this pH diagram as presented before. And we can find also we have getting all these enthalpies, and finally we may need the specific volume of state 1, which will be used in the piston displacement equation. So we have getting the specific volume of state 1, which is equal 0.09. Firstly, the COP equal H1 minus H4 over H2 minus H1, and when will we use the numbers we have getting from the chart of the enthalpies, we can get that the COP equals 3.66. M dot refrigerant, the second required in number B, equals the cooling effect divided by specific cooling effect. The cooling effect here is used 210 in kilojoule per minute divided by the delta H, which is equal 345 minus 235. We can get that mass flow rate of the refrigerant equal 1.91 kilojoule per minute per ton. Piston displacement can be estimated using the equation piston displacement Vp equal m dot refrigerant multiplying by specific volume of state 1 dividing by the volumetric efficiency, which is being stated equal to 0.8. Then we can use this equation to get 1.91 multiplied by 0.09 divided by 0.8. We can get that the displacement volume of this compressor is equal 0.214 meter cube per minute per ton. The total heat rejected in the condenser can be estimated by Q condenser equal m dot H2 minus H3, which is equal 1.91 multiplying by 375 minus 234. We can get that the Q rejected in the condenser equal to 270 kilojoule per minute per ton. The ideal COP then can be estimated using the temperature in Kelvin of the evaporating temperature Tlo divided by the temperature difference even per Kelvin or per degree Celsius. For this difference, we can get that the ideal COP is equal to 5.16. Problem number 2. A vapor compression system using RT14A works between minus 10 degrees Celsius and 36 degrees Celsius as a evaporator and condenser temperature respectively, using pH diagram to determine A. COP, B. mass flow rate of refrigerant per ton, C. piston displacement per ton using volumetric efficiency equal 83%, D. heat rejected in the condenser per ton, E. ideal COP. We can observe in this problem that the main items are required, similar to the previous problem, and also I think the same pressures, but we change the refrigerant to get different values of COP and ideal COP and mass flow rate of refrigerant per ton, specific mass flow rate, piston displacement, and heat rejected into condenser. The white area is dedicated for your solution on printed version. However, the solution will be presented on the next slide. After you have solved by yourself, you can compare between these parameters. This is the solution after presentation on pH diagram using the same pressure and temperature, using the temperature located on the evaporator and condenser. Similarly to the problem number 1, solve it using R12, but here we will use a chart of refrigerant R134A. We have get the COP. I think it has been increased compared with the previous problem, which has been equal 3.66. If we replace the refrigerant, we can get the COP is 4.66. Also, the mass flow rate of the refrigerant has been reduced from 1.9 to 1.5. The volume, the piston displacement of the cylinder of the displacement volume of the compressor VP equal m dot refrigerant multiplying by specific volume at state 1 divided by the volumetric efficiency of the compressor equal 1.5 by 0.1 divided by 83.83, which is equal 1.18 meter cube per minute per ton. Then the Q rejected in the compressor QR or Q condenser equal m dot refrigerant multiplying by H2, the entering state of the at the compressor outlet and condenser inlet, minus H3, the outlet stage from the condenser, equal 1.5 multiplying by 422 minus 252, giving that Q rejected equal to 255 kilojoule per minute per ton. Ideal COP can also be estimated using the temperature in Kelvin of T low divided by the temperature difference between T high and T low equal minus 10 plus 273 divided by 36 minus 10, which will be plus 10, giving the COP equal 5.7, which is higher than the COP of the previous cycle, which have been 5.16.
بعد أن تم استعراض طريقة تمثيل Vapor Compression Cycle on TS diagram and PV diagram and on pH diagram finally, and after solving problem number 1 and number 2, we will go through the topics of 7th lecture as started from this slide. Pressure-Enthalpy pH diagram ISO lines. This slide shows the pH diagram shown on it, saturation liquid line on the left hand side and the saturated vapor line on the right hand side. Their intersection point is the critical point at the top of this saturation line. Also, this graph have two axes. The vertical axis is the pressure in PSI, gauge pressure, or maybe in some charts in bar or megapascal if using SI units. However, the horizontal axis is enthalpy, H in PTU per pound, or for SI units it must be kilojoule per kilogram. Also, the ISO efficiency lines of temperature are shown clearly here in this pH diagram, and constant dryness fraction lines inside the vapor line. The horizontal line inside the vapor lines between the saturation liquid line and saturation vapor line, corresponding to the constant pressure and constant temperature inside the saturation region. Also, the ISO efficiency, the constant isentropic lines are shown with slope in these directions to show the constant entropy line. However, the constant volume line are shown in this direction, starting from the saturated vapor line ends, and this area is mostly used during the compression stage to detect the starting point of the compression, even on the saturated vapor line, or moved to the right some with some value for superheating process, even inside the compressor or outside, even inside the liquid suction heat exchanger or outside. and then the compression happen until reach the pressure, the horizontal line of the condenser pressure to intersect the compression line, which may be parallel to this constant entropy line or may be deviated from it if there is an isentropic efficiency less than 100%. The saturation liquid line commonly contains the out state of the condenser or with certain degree of subcooling, even inside the condenser or outside, or even inside the liquid suction heat exchanger or outside it. And then the constant H process happen to reduce the pressure to the evaporating pressure located somewhere here as per given in our problem or according to the refrigerated space requirements based on each problem, even chilling or freezing or refrigeration. The value of pressure will be evaporating pressure will be corresponding to the evaporating temperature, which must be lower than the refrigerated space temperature to evaporate and cool down the air as stated before. This slide presents the pH diagram for both R12 and R22 in black. The saturation lines are shown and also the isentropic lines are shown with constant S. The density is shown instead of specific volume. Then we can use its values to get the inverse of specific volume, or to get the specific volume if required at the end of the compressor as discussed before in solved problem. In addition, this slide presenting the pH diagram also for both R123 and R134A in black. The same values are shown, the constant S lines, the saturation line, the density in kilogram per meter cube, and the pressure on the vertical axis in megapascal, and the enthalpies on the horizontal axis in kilojoule per kilogram. This slide also presents the pH diagrams for refrigerant R407C and R717, which is named ammonia, NH3. Both charts are in black also. The saturation line is shown in bold black. The horizontal axes of pressures in megapascal are presented, and the horizontal axes of enthalpies in kilojoule per kilogram are also shown with their values, which needed to solve the cycle corners, even in case of using R407C in some problems, or in case of using R717 in another problems. The constant S lines are shown in this direction for 717 and in this direction for R407C. However, we can observe that the constant temperature lines shown here, T for example T equal 20 degrees Celsius, T equal 0, T equal minus 20, is almost vertically here, and then going horizontal constant and identical with the pressure lines, then go down in this direction for the same values. Here we can see temperature in 20 degrees Celsius here for 0 line, for minus 20 lines which started from here and then until we can find them here with constant horizontal temperature. However, for 407C we can find that these temperature lines are slightly decreased rather than constant pressure lines as usual due to the chemical composition of this refrigerant, which will be discussed during this lecture in next slides. In this slide we will compare between the same refrigerant, but we will change the color of the chart of the pH diagram, and also we will switch the units of the pressure from megapascal to bar, and the constant temperature lines are similarly and clear show and is showing clearly minus 70, minus 60, minus 50, minus 40 until reach 0, then 10, 20, 30, 40, 50, and the constant volume line are shown here in meter cube per kilogram in blue, which may be easy to be seen for the user. Also the constant temperature lines in red is shown here after going out from this vapor saturation line where it was horizontally inside the wet region and almost vertically in subcooled due to constant Cp of refrigerant in this area. We can find the dashed line in blue for constant S line, however its values are shown in this black small font as shown here, starting from 2.5, 2.2, 2.1, and therefore this is the direction of its decreasing is this direction. The direction of its increasing in this direction due to increasing in enthalpy, starting from 1.74, 1.76, 1.78, 1.8, and then until reach the maximum value of it about 2.5 kilojoule per kilogram, which is the SI units of entropy commonly used to detect the isentropic efficiency value in compression process inside the compressor. In this slide we will compare between the widths of the cooling effect, which is indicated between the saturated liquid line and saturated vapor line for both R22 and R134A. It should be clear that the width of R22 between the two saturation lines are larger for the same pressure than it recorded here for R134A, which means that the M dot refrigerant for R22 for the same cooling load will be less than if using R134A, which for sure will increase the COP of the cycle if using R22 compared with R134A. However, the chemical composition of both of these refrigerant, which we'll discuss in next slides, giving R134A better performance due to its ODP and GWP, which we'll discuss also in next slide. We can observe that R134A is HFC, which means it contains hydrogen, fluor, and carbon without chlor. However, R22 is HCFC, which is hydrochlorofluorocarbon. It means it contains hydrogen, chlorine, and fluorine, and carbon. So the presence of chlorine atom in R22 makes it out of service in recent years due to its chemical composition if compared with R134A, as will be discussed in this lecture. Here in this slide we enlarge the pH diagram, the colored pH diagram of R134A, to make it visible clearly during solving our problems. We can review on it the main items and the main lines must be shown on the pH diagram, such as the vertical axis of pressure in bar, the horizontal axis of enthalpy in kilojoule per kilogram, the liquid saturation line until critical point, and then the vapor saturation line with this slope, which is larger than the slope of liquid saturation line. And then we can find the constant temperature lines, which must be plotted here in vertical lines due to constant Cp as mentioned before, but its values is shown here starting from 0, 10, 20, 30, and here minus 10, minus 20, minus 30, and then it will be continued here again on the saturation vapor line starting from 0, 10, 20, 30, 40, 50, and in the other direction, negative direction, starting from 0, minus 10, minus 20. The constant S line are shown in blue here with the same values range starting from 1.7 up to up to S equal 2.25 as shown here. The constant specific volume lines are shown in this direction, even inside the wet region and outside in the superheated region, and its values starting from here and increased in this direction until reach specific volume equal 0.02, and in units, its units in meter cube per kilogram, and its values can be also read from here. On this vertical axis. In this slide we also present R407C, which is commonly used, however, in color. However, the decreasing of the temperature line inside the wet region are also observed clearly here, rather than the black one presented in the previous slides. The constant S lines are shown here in blue, and the constant specific volume are shown in green, and the constant temperature lines in superheating region are shown in red, and its values is listed here. The values of enthalpy are listed here in kilojoule per kilogram in this line. The pressure values in bar in this vertical direction. The values, some values of entropy are still shown here in blue, starting from S equal 1, S equal 1.2 line with a stepped, with 4 lines stepped in between. So The next line for 1 is 1.05, then 1.1, 1.15, and finally 1.2. And also it can be read from here easily inside the superheating zone to estimate the compressor performance and the isentropic efficiency value and the deviation from isentropic compression process if listed in any problem. These charts are dedicated for R401A in color also. We can find the same ISO lines, and we confirm here that the temperature lines inside the wet region are horizontal and identical and typical to the constant pressure inside the wet region for this kind of refrigerant, which is recommended rather than 407C due to its stability and its stability for condensation temperature and evaporating temperature rather than 407C as discussed in the previous slide. Values during the solution. In this slide we will compare between the isentropic and real compression in a log pH diagram. We can find here the starting point of compression, which is located on the saturated vapor line, and in case of isentropic efficiency equal 100%, and for isentropic compression we will use this red line to get H2, which must be located also on the condenser pressure, the second location for this line, and the first location is constant S line. Based on S2 must equal S1 using this constant S line shown in red. However, if the problem have isentropic efficiency less than 100% and the compression process is not isentropic process and just adiabatic process or non-adiabatic and non-isentropic, sure, then the constant the process line, the compression line, will be go to the right of the constant S line with the difference, which makes the projection area of the compression from 0.3 to 0.1 will be larger than the projected area of isentropic compression, with this difference which increase the work of the compressor, and that will affect badly on the COP and decreasing the COP due to the actual of the cycle compression, the actual of compression process happen inside this cycle, and the effect and switch the COP of the simple cycle and ideal cycle to be a real cycle when implementing the effect of the non-isentropic compression into our. The red compression line in the attached figure supplies an ideal isentropic compression at constant entropy in which there is no heat exchange with the surrounding. In reality, however, there are always some heat loss or losses from the vapor due to the mechanical friction in the equipment, flow frictional work between the fluid and the wall, and potential leakage in the compressor. The shown figure illustrates a comparison between realistic case, which is shown in blue line, and the theoretical isentropic compression, which is shown in red line. The difference between isentropic and the actual compression can be expressed by an isentropic compressor efficiency eta isentropic. Now we will switch to the selection of the right refrigerant type type of refrigerant determined by the required cooling temperature, chlorinated fluorocarbons, CFCs or ferrions, R11, R12, R22, R21, R402. This is the name of the CFC of chlorofluorocarbon or chlorinated fluorocarbons, or may be named as a ferrions if it contains CFC. To select the appropriate refrigerant, their ODP, ozone depletion potential, and GWP, global warming potential, need to be considered. The effects of each type of the selected refrigerant must be selected carefully based on its impact on the environmental point of view and its effect on ozone layer and the global warming potential on the earth. The selection process must be based on the corresponding features which must be taken into consideration: the choice of compressor, the design of condenser and evaporator, and should be determined based on refrigerant type, required cooling load, the cooling load, ease of maintenance, physical space requirements, and availability of utilities such as water and power. If using water cooling system or air cooled system, the air must be provided in air cooled system with the amount enough to remove the heat rejected from the condenser side. Also, in water cooled systems, for the condenser, water must be provided with a certain amount, taking into consideration the costs of running water and the temperature increasing of this temperature between the supply cooling water temperature and return water temperature, that may require to add a cooling tower or to use seawater or river water or raw water, some kind of raw water. Also, the power to be provided to drive the circuit, the refrigeration circuit, must be considered into consideration, and its initial cost requirements and running cost requirements should be taken into the break-even analysis should be made on the cycle, which all of these parameters will be based on the type of refrigerant that you have selected to carry out the load and acting as a working fluid inside this refrigeration cycle, especially which based on vapor compression cycle. This slide also indicate what is a refrigerant. The refrigerant, it should be clear from this slide, is a medium or a working fluid is selected carefully to move the heat from the refrigerated space and to be reject the heat to the surrounding, even via water or via air. Also, the refrigerant is a substance that absorbs heat by evaporating at low temperatures and pressures inside the evaporators, and then gives up the heat by condensing at high temperatures and pressures in the condenser. So it should be clear the effect and the value of the evaporating temperature and its reducing will affect the amount of the refrigerant, as can be seen on the previous presented pH diagrams, with different cooling effects, with different widths between saturation liquid line and saturation vapor line. Also, the condensing temperature, which will correspond to condensing pressure, even using water or using air, that will affect the value of the condenser pressure, and then the power required by the compressor, and the cooling effect will be slightly affected by the value of the condensing pressure and may be increasing due to the slope presented before and discussed before for the saturation liquid line from the left hand side of the cycle at the end of the condenser, which will be increased if using water rather than using air. However, the increasing of the work when using air cooled condenser will also decreasing the coefficient of performance of this cycle, and some problems will be comparing between air cooling and water cooling for certain type of refrigerant to study the effect of the cooling media to transfer heat from the selected refrigerant of this vapor compression circuit, and also with taking into consideration the initial cost of this additional system components which must be required to be connected in water cooled systems, such as cooling water pumps, cooling water pipes and valves and fittings, and finally the cooling towers. This slide classify the alternative refrigerants into three types: HCFC with chlorine, and HFC with no chlorine, and halogen free, such as pure ammonia or propane or mixture of propane and isoputane. The HCFC, which is without chlorine, if it pure, such as R22, and it may be mixture such as R10A, which may be named in some marketing companies as a boron refrigerant. However, hydrofluorocarbon also with no chlorine, if it pure, such as R134A, or maybe mixture of these HFCs such as R407C, that may affect the evaporating temperature stability inside the wet region, as can be seen on the presented pH diagrams in the starting of this lecture. The suffix or prefix of each and the abbreviation of each type, CFC, it's shown in the tableau shown below: CFC, HCFC, HFC, and finally HC. CFC means the first C equal to means that there is chlorine atom, F for fluorine, and finally C for carbon. HCFC, hydrogen, chlorine, fluorine, and carbon. HFC, hydrogen, fluorine, and carbon, and finally hydrocarbon, hydrogen, and carbon. So CFC means chlorofluorocarbon, HCFC hydrofluorochlorocarbon, HFC hydrofluorocarbon, HC hydrocarbon. Refrigerants are divided into groups according to their chemical composition, following the discovery that some of these chemical compounds may be harmful to the environment. They are being replaced with more environmentally friendly alternatives. The process is not easy, and although there are alternatives to replace old refrigerants, the new ones are usually not flawless. In the following section, different groups of refrigerant are discussed, some examples are given, and their fields of application are described. This slide presents the tables presented on the chapter 20 of ASHRAE, which is with title Thermophysical Properties of Refrigerants. This table gives the table of contents of the refrigerant in this slide and the next of it for the different type of refrigerants, starting from halocarbon refrigerants, which have been grouped here: methane series, ethane series, and finally propane series. These types of halocarbon for methane series are R12, R22, R23, R32. For ethane series, R123, R123, R124, R125, R134A, R152A, and finally R143A. For propane series, R245FA. Some another types of refrigerants, such as and named zeotropic blends by mass percentage, 400 series. The zeotropic is a 400 series as shown here, starting from R404A, R407C, and R10A, which is named boron. Each one contains different halocarbon refrigerants, which is based on R125, 143A, and 134A, with different percentage by mass. Then we can find R407C contains R32, R125, R134A with different mass percent, starting from 23 for 32 R32 and 25% for 125 and 52% of 134A. So we can observe that R404A and R407C are containing R134A, but 404 by 4% of mass, however 407C by 52 by mass percentage. R410A consists of two refrigerant only, R32 and R125 by 50% of mass percentage. Azeotropic blends, which 500 series, for example of it, R507A, which contains R125 and R143A, 50% by mass. The details of these refrigerants will be discussed here in this lecture in next slides. This slide continues the table of contents presented in the starting of chapter 20 of ASHRAE, thermophysical properties of refrigerants, but presenting the different types rather than the halocarbon refrigerants, such as inorganic refrigerants, such as R717 ammonia, R718 water and steam together with the same chemical composition H2O, and finally R744 carbon dioxide. It should be clear that this is 700 series of inorganic refrigerant series. Then we will switch to hydrocarbon refrigerants, which based on pure hydrocarbons such as methane, ethane, propane, N-butane, isobutane, ethylene, and propylene. R50 is the methane, R170 ethane, R290 propane, R600 N-butane, and R600A isobutane, and R1150 ethylene, and R1270 propylene. Then we will switch to some cryogenic refrigerant. Also, it's inorganic. We can consider it as inorganic, so it is relative to the 700 family. R7O2 normal hydrogen, R7O2P para hydrogen, R7O4 helium, R728 nitrogen, R729 air, and R732 oxygen, and finally R740 which is argon. The absorption solution, not refrigerant, we can name it as a solution, which will be used in absorption cycles, vapor absorption cycles, which will be discussed in lecture number 10, can be classified into the main solution, or may be named also as a refrigerant, such as ammonia, water, one of them acting as a solution and one of them will be acting as a refrigerant. Then water, lithium bromide. So the water will be the refrigerant and the lithium bromide will be the solution. According to an international agreement, refrigerants are presented by letter R as a refrigerants, followed by a 2 or 3 digit number, and in some cases 1 or 2 letters. The designation of RXYZ is determined by the chemical composition of molecules and as described below. Firstly, we will start for methane, ethane, propane series. Here X gives the number of carbon atom in the chemical formula -1. If X equals 0 is for methane series, but the 0 is ignored for these compounds such as R12 and R22. Then if X equals 1 is the members of the ethane series, where the carbon atoms is equal to -1, then the X will be 2 minus 1 equal 1. Then it will be from 100 series such as R114, R and R124, and finally R134A. If X equal 2 is for propane series, which contains 3 atoms of carbon -1, then X will be 2. For 200 such as R290, which is named propane. For these groups, Y describes the number of hydrogen atoms +1 and Z describes the number of fluorine atoms without plus or minus. CFC, chlorofluorocarbon. Chlorofluorocarbons are refrigerants that contain chlorine. They have been banned since beginning of 90s because of their negative environmental impacts. Example of CFCs are R12, R11 and R115. The conversion of equipment and systems using CFCs has not yet been completed. On contrary, the eagle market for this type of refrigerant flourishes worldwide, and it is estimated that no more than 50% of CFC systems worldwide have been upgraded. HCFCs, hydrofluorocarbons. The slow phase out of CFCs shows it is a costly process. However, and more importantly, it also shows the problems and indecisiveness surrounding the availability of HCFCs, which were officially indicated temporarily until 2030, substitutes for CFCs. The hasty actions of the European Union that culminated in the ban of HCFCs immediately for refrigeration and soon 2004 at least for air conditioning has upset the industry's program and plans. The HCFCs contains less chlorine than CFCs, which means a lower OTP. Example for hydrofluorochlorocarbons includes R22, R123 and R124. Hydrofluorocarbon. The hydrofluorocarbon are refrigerants that contain no chlorine and are not harmful to the ozone layer with ODP equal 0. However, their impact on global warming potential is very large compared with traditional refrigerants. The most common HFCs refrigerants available since the ban of HCFCs are presented. Fluorochlorocarbons FCs. Fluorochlorocarbons contain no chlorine and are not harmful to the ozone layer. However, they are extremely stable and they have a high GWP. R218 is an example of fluorocarbon, and FCs are also presented in the mixtures R403 and R408. This slide is dedicated for comparison between the banded R11 and R12 with the replaced R123 and R134A. The typical characteristics and application are listed here. For both of banded refrigerants R12 and R11 and their replacement with R123 and R134A. This slide presents some of halocarbon refrigerants such as R13, R113B1, R114, R143A, and R125 and R152. The temperature range and the application of each type are listed also within this slide for your attention. Other refrigerants. Recently, a type developed azeotropic refrigerant. Mixed refrigerants are mixed in a certain ratio of two refrigerants where in a single refrigerant such as a MAD available refrigerant. Evaporation and condensation are no changes in the structure during. In system where the compressor is directly connected to the electrical motor, the power source frequency changes, the cooling capacity varies. This change can be avoided if azeotropic refrigerant is used. Salt solutions donors at low temperatures from freezing point of pure water. Chilled saline solution with direct coolant is transported by pipe to the cold storage of ice making system, taking heat from the material to be stored in a cold and cools them. It's most commonly used with calcium chloride brine solution. This slide will compare between zeotropic mixtures of 400 series and azeotropic mixtures of 500 series. For zeotropic mixture firstly of 400 series, the X number of included in RXY number of each refrigerant will be 4. So all of these family will be starting with number 4 at the first digit, replacing the X. So all types will be 400 series. The components in this mixture have different boiling points, and thus the refrigerant mixture have been a temperature glide. R407A and R407C are examples of such refrigerants. Capital letters describe specific mixing proportions of different components. For example, R407A to E are mixtures of refrigerants R32 and R125 and R134A. However, the percentage of mass of each of these three components are different from R47A until R47E. For example, R47A has the following mixing proportions: 20% of R32 and 40% of R125 and 40% of R134A, while R407C consists of 23% of R32 and 25% of R125 and 52% of R134A. It should be clear that the same components of basic refrigerants are used, however, the percentage of each of them inside each type of these deotropic refrigerants R407A and R407C is different during to its composition by mass percentage. Then we will switch to azeotropic mixtures of 500s which have X number equal to the 5, which refers to 500 series. These acts like homogeneous substances with one specific boiling point, and therefore they have no glide in the temperature. So R502 and 507 are examples for azeotropic mixtures. Here Y and Z are ordinal number. This slide presents the different types of azeotropic of 400 families and its composition from different type of refrigerants by mass and the basic refrigerant composition. It should be clear that this composition and these mass ratios affect the glide of the temperature inside the wet region as have been presented for most of them, especially for R47C in its pH diagram presented at the starting of this lecture. Also, this slide will present the commonly used azeotropic refrigerants of 500 series such as R500 and R502 and R507, which consists of R125 and R134A. However, R500 consists of R12 and R52A with different components, 73.9 and 26.2, and R502 is a azeotropic mixture, consists of R22 and R115. The mixture rate in terms of weight is 48.8% of R22 and 51.2% of R115. This is the mostly used refrigerated transport and commercial refrigerant equipment. Its manufacture has been stopped because it contains CFC, which contains in R22. It has a volumetric capacity at low temperatures between -20 and -40. It is 1 to 7% higher than R22. Depending on the working conditions, COP values is 5 to 15% lower than R22. which is the most recommended COPs before it have been banned as per European Community and their Montreal Protocol in this subject. This slide concluding in this table the zeotropic refrigerants and their composition by weight of different refrigerant used for each type, even two refrigerant or three refrigerant for the zeotropic of 400 series, and also the same for the selective of azeotropic refrigerant shown in blue in the below rows in these tables of 500 series and their composition of the two used refrigerant to conclude the previous two slides. High organic compounds of 600 family, which contains X equals 6, means that the composition is organic, such as butane R600 and isobutane R600A. This group has several subgroups, for example hydrocarbons, oxygen compounds, sulfuric compounds, and nitrogen compounds. The subgroups have been assigned different number series within the main group, so Y and Z describe the subgroup and order within the subgroup. Letter at the end, the last letter, if any, is in the designation of the number means different things. Lowercase letters describe the structure of molecules. For example, R600 is butane and R600A is isobutane. These two compounds have the same chemical formula but different sepal arrangements, and they therefore have slightly different properties due to this sepal arrangement in their chemical composition and arrangement between carbon atoms and hydrogen atoms inside this butane compound. Hydrocarbons. The hydrocarbons are very limited solution to the environmental problem associated with refrigerants. They are harmless to the ozone layer, ODP equals 0, and have hardly any direct greenhouse effect with GWP less than 5, but they are highly flammable. The use of hydrocarbons, which nomenclatures HCs as refrigerants, is confined to Europe because many other countries elsewhere have banned to use the flammable gases in the presence of the public. According to the standard ISO 55149 and EN 378.2000, this should apply also in Europe. However, the standard IEC 355.2.20 allows the use of HCs in household refrigerators with refrigerant charges up to 150 gram. This standard has opened the way for the same European refrigerator manufacturers to produce household refrigerator with flammable isobutane R600A. These have been accepted by environmentalists and have achieved great successful in the market. Inorganic compounds 700s family. When X equals 7 refers to inorganic compounds such as ammonia, water, and carbon dioxide. In this group, Y and Z are the molar mass. For example, NH3 contains 1 nitrogen atom and 3 hydrogen. The weight of nitrogen is 14 and the weight of hydrogen is 1, so 14 plus 3 hydrogen equals 17. So the 700 family for ammonia will be named as 717. For water, H2O, 2 atom of hydrogen and 1 of oxygen equal 16 plus 2 equal 18. For CO2, 1 carbon atom equal its weight equal 12 plus 2 of oxygen equal 16 by 2 equal 32 plus 12, which gives 44. So the carbon dioxide will be named as described in previous lecture problem of CO2 R744. Unsaturated organic compounds 1100 series. When X equal 11, starting from 1100, stands for unsaturated ethane compounds such as R1150, R1150, ethylene. Where X equal 12 stands for unsaturated propane compounds such as R1270, propylene, which have number 1270. The Y and Z are the same as for the ethane and propane series. Ammonia, which is named R717, is an attractive refrigerant alternative. It has been used for refrigeration systems since 1840 and in vapor compression since 1860. In terms of its properties, it should be considered a high-class refrigerant. Furthermore, its ODP and GWP are zero. However, also its sulfurating gas leaks can easily be detected by the smell. Ammonia is very hazardous and have its large hazard even at low concentration because the smell often causes panic. This is the main reason why ammonia was withdrawn from applications for use by unskilled people and retained only for industrial application. It's also quite common in commercial refrigeration, although safety regulations require that it be used with a secondary distribution loop. Obviously, the secondary loop reduces the efficiency. NH3 is colorless gas containing nitrogen and hydrogen. Chemical formula NH3 containing nitrogen, and the rest of the slide contains some thermophysical properties and chemical pattern of NH3 for your concern. R744 CO2 carbon dioxide has several attractive characteristics. Non-flammable, doesn't cause ozone depletion, very low toxicity index, safety class A1, available in large quantities, and low costs. However, it also has a low efficiency, a high operating pressure, approximately 10 times higher than R134A, as can be seen in the solved problem at the end of lecture number 6 presented before. For these two latter reasons, efforts are needed to improve its refrigeration cycle and related technology, particularly heat exchangers and expansion devices. A major forthcoming CO2 application seems to be air conditioning in the automotive industry. Heat pumps could also benefit from CO2 due to higher temperature that can be obtained even at very low ambient temperatures, as can be seen on the problem solved at the end of the previous lecture number 6. Finally, the features which coolants must have, or our refrigerant, or our basis on which our selection must be performed carefully to select the right refrigerant according to the heat pump or the refrigeration machine will be under consideration or during design stage must consider the following features as listed in this slide. They must evaporate and liquefy under applicable pressures. Its evaporation temperature must be low. Chemical dissolution and burning must not happen. Also, they must be not toxic and react to touch with the metal surfaces. They must work under low powers. Their cost must be low and provided easily. They must work under low powers. They must oxidize the pipe when they are in. This slide finally concludes the main features from point of view chemically and HSE, health and safety and environment, and thermal conditions and other requirements to be taken into consideration during selection process of the right refrigerant according to the typical application or typical cooling load. From chemical point of view, it must be stable and inert. From HSE point of view, it must be non-toxic, non-flammable, benign to the atmospheric. From thermal conditions, critical point and boiling point temperature appropriate to the applications, low vapor heat capacity, low viscosity, high thermal conductivity. Other features: satisfactory oil solubility and miscibility, high dielectrical strength of vapor, and low freezing point and easy to be detection for leak detection, and low cost and reasonable materials to be used to contain this type of refrigerant. Which coolant are used most in the cooling system with Freon? In these procedures, storage spaces of living spaces are cooled by means of conveying the heat from the source in low temperature to the environment in high temperature. That is the theory of the vapor compression cycle of any refrigeration machine. The heat normally moves from high temperature to low temperature. This is the theory of heat transfer concept, that the heat must transfer from the high temperature level to the lower temperature level. Therefore, insulation has a big importance on the procedure carried out. Therefore, insulation materials with low heat transmission coefficient are used. Polyethylene is the most important thing used frequently in today's system. Insulation is used to protect the low temperature in the cooled space and to reduce the energy and the power required to reach the low temperature. The working principle of the cooling cycle was mathematically defined by Sir Carnot with the heat machines in 1824. Since about 200 years ago, the most general cooling system used in the cycle based on the heat pump with phase change. Also, absorbing heat pumps are used in most of these procedures. A working fluid in a compression refrigeration system must satisfy a number of requirements that can be divided into two groups. The refrigerant should not cause any risk of injuries, fire, or property damage in case of leakage. 2. The chemical, physical, and thermodynamic properties of the refrigerant must suit to the system and the working conditions at reasonable cost. It is not possible to fulfill all the requirements above at the same time. The most important criteria is chemical stability within the refrigeration system, and all other criteria are meaningless if the refrigerant decomposes or reacts with the material used in the system. However, the chemical criteria can also be a problem. When a refrigerant is emitted to the atmosphere, it should not be so stable that it can exist indefinitely. The ideal refrigerant would be totally stable in use within the system but would decompose easily in the atmosphere without the formation of any harmful substances. The thermodynamic and the transport properties determine the performance of the refrigeration system. The pressure should be neither too high nor too low. A pressure below atmospheric is undesirable because air can then be sucked into the system, resulting in problems such as inert gases in the condenser or ice plugs in the expansion valve, as this problem has been detected when using R11 because its pressure is lower than the atmospheric pressure in the evaporator. So when any leakage happens, the air go inside the cycle and damage its performance rapidly, and consisting of ice inside the cycle due to icing formation within the working fluid going through the cycle and its components, and plugs the piping and the condenser and makes the cycle to be stopped. The latent heat multiplied by the vapor density gives an estimate of the capacity of the refrigeration system. A refrigerant with a high pressure gives a high capacity, but a refrigerant with low critical pressure compared with the pressure in the system leads to a low coefficient of performance COP. This trade-off between heat capacity and heat efficiency and high efficiency must be considered when choosing the refrigerants. This is your responsibility as a designer of the certain system to compromise between the selection of the equipment and the refrigerant and its capacities and the efficiency generated due to this selection based on the initial cost and running cost. Another desired criteria is that the specific heat should be small compared to the latent heat of vaporization in order to achieve small losses in the expansion device. Oil is normally present in a refrigeration system, and the interaction between the oil and the refrigerant must be considered. High oil solubility is used in hermetic compressor, but immiscible oils are normally used when the working fluid is ammonia. Thanks for watching this lecture about selection of the right refrigerant, and we will see you in next lecture inshallah, lecture number 8 about the residual innovative vapor compression cycle, starting from cascade cycle, multi-stage compression cycle, multi-evaporator with multi-stage or single-stage cycle, and gas liquefaction. And then will we go to lecture number 9 to solve problems based on this residual innovative vapor compression cycle. Thanks for watching. Seeing you.